is my domain, domain. You're in my kingdom now. This is my domain, domain. No one can tear it down. This is my domain, domain. You're stepping on my ground. It's live or die my way. Inside the walls of my domain.
Hi, in this video we're going to do more examples where we find the domain and range. And now we're going to find them from graphs, and then we'll find them from the function formula. All right, so remember from our last video that domain means x values and range means the y values. And another way to think about that is domain is the valid inputs, while range is the valid outputs. So to get us started, I have a few graphed examples, okay? Remember when we talked about the domain, we talked about building the walls on the house. All right, domain is our x values. We know that our x-axis goes side to side. So we want to think about the smallest x value for which this takes on. Okay, and then the largest x value for which this takes on. Well, I can see here the solid dot means this function starts here. So the smallest x value for which this is defined is going to be -3. Okay, and now it's a solid dot, so we want to use less than or equal to, and we're talking about x. So I'm going to use the variable x, domain x. Okay. All right, and now when I look over here, it looks like I could build a wall here, but what we know about arrows on the end of functions is they keep going. Energizer bunny, going and going and going. So even if I tried to build the wall here, it would go on the other side. Build the wall here, it would go on the other side. So this is going to keep going. And so every x value would be eventually defined out to infinity. So my domain here, if we want to stick infinity on this side so we can see it, means that x is going to always be greater than or equal to -3 to infinity. And the proper way of really writing this is -3 less than or equal to x. In other words, x is always greater than or equal to 3. As long as we pick an x value greater than or equal to -3, this function will be defined. All right, when we talk about the range, remember we're talking about the ceiling and the floor, or in other words, our valid y values. I want to look at for the smallest y value this function ever takes on, and I see that if I put a floor here, the function would never drop below it. So that value is going to be -4. And now I'm going to use y, range y. And now if I try to build my ceiling, the same thing's going to happen as happened with x. If I build it here, it keeps going. If I build it here, it keeps going. So up here, we have positive infinity. So if we want to write less than infinity, all right, just to show that y is defined from -4 to infinity, we sure can, but it's more proper to write it this way. Okay, so that is from a graph. Let's do one or two more examples. All right, so here I have this function. We're talking about the domain. We're talking about the range. Domain walls. If I want to fence this in, well, notice this has arrows, and even though it's going up really, really slow, I can see, though, that eventually this function would be defined for every x value. So one way of writing this is all real x, okay? There's lots of different ways to write this. Interval notation, it's -infinity to positive infinity, and this just means every value of x, this function is defined. How about the range? Well, for the range, we're going to think about our y values. Can we construct a floor that this never goes below? And sure enough, it looks like that I could build a floor right there. And now in this particular graph, 1, 2, 3, if we can read it off exactly, great. If we can't, I'm just going to approximate that to be -3. Okay. And now how about our ceiling? Well, if we build our ceiling here, it's still going to continue to go on. Okay, so we can never put a ceiling on this function. It's going to keep going and going and going, and we know that this goes off to positive infinity, so this is going to be less than infinity. All right, probably the most proper way of writing this is this way. okay? And now later on we'll talk about interval notation, but we're not quite ready for that. And if you know interval notation, please feel free to use it, okay? All right, our last graphing example is going to be this one. Again, we want to talk about the domain and talk about the range. All right, so if we try to put our walls on here, this is going to keep going and going and going. This is going to keep going and going and going. And we see that this would be defined for every x value, okay? In other words, just like we've been saying, it's defined from negative infinity to positive infinity. And now if we go to look for a floor, well, we can't put a floor there because it's going to keep going. And we can't put a ceiling here because it's going to keep going. So you see that in this example, the range also is going to be negative infinity to positive infinity. Okay, so every value is defined on this graph. Okay, so that's an example of how all real numbers would be. All right, now on the graphs it's kind of easy to see, but what if we give you the formulas and not the graphs? So I have 3 examples here. Option number 1, and it's always a good option, especially in today's age, is option number 1 is to graph it, just like we've done. Okay, and look for the domain and range. All right, so if I go to a graphing tool, and I'm going to use GeoGebra, all right, I can just type in my function as is, f of x equals minus x. We use the caret key for squared, plus 5x, and then minus the 6, okay? Now I have it on this graph, and I can zoom into the graph, okay? If I want to be exact, I can put a point right here, all right? And what I see on this graph, if I'm trying to define the domain and range, if I zoom out, I see that it is going to be defined for every x value. So my domain is going to be all real x, okay? And now if I try to use the graph to define my range, I can do that as well. It looks like I could put a ceiling right here. It's approximately 2.5. And then this would go on down to negative infinity. So my range in this case would be y less than or equal to 2.5. Okay? All right, we can look at our second example. This one's going to be a little harder to see from the graph. But what we know about a function is we can't have what in the denominator? Okay? We can't have a 0 here. Why can't we have a 0 in the denominator? Remember that that makes our function undefined. So when we have a denominator in our function, and we're talking about the domain, all right, and that's primarily what we're going to want to define for this, all right, we want to start off by saying all real, but if we have our variable in the denominator, we're going to have an exception, and the exception becomes whatever value we can plug in here that gives us a 0. So in this case, it's going to be x equals 7. In other words, I cannot plug in 7 here, okay? And because if I do, I get 5 over 0, and that's undefined, okay? Every other value works. And now if we go back to our first example, notice that we don't have a denominator. I mean, we in theory do, it's 1, but we don't have to worry about it. And that's why if you don't have a denominator or a radical, we're going to talk about that in the next example, your domain is going to be all real numbers or all real x. If you have a denominator, the variable in the denominator, you have to exclude any values that would give you a 0 in the denominator, okay? All right, there is an exception to that. This needs to be in simplified form, but we're not going to worry about that today, okay? So if we are given a variable in the denominator, we need to exclude any values that would give us 0. And in this case, it would be 7, because 7 minus 7 is 0, and that would give us something undefined. And now I just referred to a radical. What do we have to worry about here? Well, for radicals, we can't have a negative under the radical. Now, you may have already talked about the imaginary unit and those types of things, but when we're talking about real numbers, all right, for the domain, we can't have a negative here, underneath here. So our domain in this case, we could actually set this up. We know that that has to be greater than or equal to 0, right? And if we solve this, we would see that x is greater than or equal to 3. So that would be our domain. Another way to see this is if we graph this, you could see the domain pretty easily. All right, so I'm just going to replace our graph with the SQRT square root of x minus 3. Okay, and now you can see here that my function would start at 3. Okay, and it's defined for every x greater than 3. All right. And now you can see that as well. And now from the graph on this one, we can determine the range as well. It would be 0 off to infinity. And yes, it goes up slowly, but it would eventually get to all numbers. Okay. So when we have a formula, a couple of things to keep in mind. Number one, you can always graph it. This one, the second one, would not really work for the graph because we're only excluding one point, and that will not show up on the graph. All right, so what you need to do is remember that if we have a variable in the denominator, we have to exclude, any x values that would give us a 0 in the denominator. And if we have a radical, we have to define our domain to be the x values that only end up giving us positive numbers under the radical. I hope these examples help. Good luck finding the domain and range.
This is my domain.